So imagine a rabbit bouncing around on your front lawn. And if the rabbit is big and fat and predictable, he's not going to last very long because the local cat will pounce on him and eat him up. Around the woods, the fox will find him. The most survivable rabbit is the one that's unpredictable, the one that jumps, and his jumps are chaotic, unpredictable. And therefore, unpredictability means survivability in the gene pool. So it's not surprising that we see evidence of chaos in some living animals. We've done this analysis, and we've shown that nerve cells in some animals behave chaotically. So, okay, that's interesting, but it turns out that there are some applications that save the government lots of money. And by lots, I mean not bankers' kind of money, but only hundreds of millions of dollars. So here's the story. In 1991, the Japanese wanted to become the third nation to send a rocket to the moon. They designed a probe and launched the probe. And the idea was they're going to send a mothership up to an orbit around the Earth, and then from the mothership, launch a probe to the moon. And when the probe got to the moon, it would go into a parking orbit around the moon, relay data back to the mothership in a parking orbit around the Earth, and then that satellite would downlink the data to the Earth. So it's a two-spaceship mission. The probe had enough fuel to get to the moon and do some course correction maneuvers, and the mothership had enough fuel to get to the parking orbit. That was used up by the time it got to the parking orbit, plus a little bit left over to make some corrections over the course of the next 3 years. So the ensemble got to a parking orbit around the Earth, and then the moon probe was launched. And when it got to the moon, we lost contact with it. The communication channel went dead. Nobody knows what happened to the probe. So here are the Japanese with a missing probe on the way to the moon, and the mothership in parking orbit around the Earth, and unable to claim that they're the third nation to get the moon, bomber. So it was a bad day in Japan. Then somebody remembered that there used to be a guy working at NASA who investigated trajectories in the solar system based on nonlinear dynamics. And these trajectories had the advantage that they would make use of certain strange things, called stable and unstable manifolds, that exist in the solar system to get from A to B at almost no fuel cost. He did this for a couple of years at NASA, and because that wasn't what NASA was looking for, his enthusiastic hard work was rewarded with the standard reward of somebody who was too far ahead of his time, expired. But somebody remembered that he did this work and asked, hey, can you design a low-energy orbit, transfer orbit, from the moon to the Earth for this Japanese satellite, which has a thimble full of fuel on board? His name is Bruno, and he's written a book called Fly Me to the Moon, because that's exactly what he did. We've written some books, too, on chaos. This is one, but I want to talk about this guy's work here. What he did is show that you can find trajectories in the solar system that get from A to B at very low fuel cost, in other words, cheap, if you're willing to wait long enough. And he designed one that the Japanese bought and used. It took 5 months as opposed to the standard 1.5 to 3 day transfer from the Earth to the moon. It took 5 months to get from the Earth to the moon, and it went around Robin Hood's barn, literally around Robin Hood's barn, but it did what was needed. So the orbit, the satellite in the parking orbit was transferred to an orbit way out here, went around a bunch of times, and then followed this ensemble of trajectories. You can see that there's a splitting point here. Some of these fold this way, some of these go this way, And he picked one that went right around to the moon's orbit, and when it got in the neighborhood of the moon, it expended a tiny bit of fuel to park itself around the moon. Stayed there 2 years, took data, relayed back to the Earth. There's no relay satellite by now. And at the end of its useful life, the Japanese purposely crashed into the moon so that they could test some lunar internal vibrations. This technology is now beginning to be used to design other trajectories in our solar system. The Genesis trajectory is done like this. This is an infrared telephone facility that was designed in the same way. There are now 5 trajectories that depend on all of these bizarre, can't believe it, bizarre ways to design interplanetary trajectories. Okay, so here's where we were. And these depend on, how are we doing on time? No minutes left? Finished? Okay, so this is a picture of the interplanetary highway system. And these are all very low energy, very low cost trajectories. You can see the interchanges occur in the neighborhood of each of these planets, whether you count 8 or 9 or 10 planets. This is where the interchanges occur. So you can follow one of these, and when you get to the neighborhood of a planet, there'll be off-ramps and on-ramps to other roads. And the beauty of this is that as time goes on, the planetary positions change. So this interplanetary highway diagram morphs. That means that if you can predict where the interchanges are going to be, and then get your spaceship to that interchange, then as you approach, the interchange will be created. You get there, you can get off, get on, and then after you leave, that interchange disappears. So this is a moving thing, and we're just beginning to understand how this interplanetary highway system works, and it's all based on the laws of nonlinear dynamics. So I think we're out of time. I thank Tim for creating these masterpieces, and hope you enjoy the rest of the day.